Hello everyone, welcome to the fifth lecture of the series on AI using Python. In this lecture, we discuss about polynomial regression with some examples in Python. In general, polynomial regression is used to model nonlinear input-output relationships. So it can be considered as an approach that comes under the category of nonlinear regression. In polynomial regression, we fix the input-output data with a polynomial function which can be represented as in this equation, where x is the input variable and y hat is the predicted output, and f is the model, which is in the form of a polynomial function as shown here. Here p0, p1, pm are the coefficients of the polynomial, which acts as the free parameters in the model. And capital M can be considered as the order of the polynomial. In general, polynomial functions can approximate any continuous and infinitely differentiable functions with sufficient accuracy. This can also observe from the Taylor series expansions, and this makes the polynomial functions as a good candidate for regression models. In polynomial regression, our objective is to find the optimal parameters that fits the input-output data in the best possible way. And for that, we can use the available data or the training data, which consists of n observations of the input samples, which we denoted by x1, x2 up to xn, and n observations of the outputs or labels, which we denoted by y1, y2 up to yn. Next, we can consider an example to illustrate polynomial regression. And here we are considering the data is generated from a polynomial function, which we have already discussed in one of the previous lectures. The training input consists of 10 equally spaced data points between 0 and 1. And the training output is generated using the polynomial function, which gives ytr is equal to 0.02 xtr cube plus 0.1 xtr square plus 0.5 xtr plus 2 plus r, where r is a Gaussian random variable with mean 0 and variance 1. Now we can move on to the code, and we start by importing the NumPy and Matplotlib libraries. Then the input data x is defined as 100 equally spaced data points between -10 and 10. And the output y is defined as a3 into x cube plus a2 into x square plus a1 into x plus b, where a3 is equal to 0.02, a2 is equal to 0.1, and a1 is equal to 0.5, and b is equal to 2. Here we consider this y as the actual output, and this is the actual model, and these parameters a3, a2, a1, and b as the actual parameters in the model, which are considered to be unknown. Then we generate the training data by adding some uncertainty to this model, and for that we are using the random state function from the NB library. Then the training input xtr is defined as 20 equally spaced data points between -10 and 10, and the training output ytr is defined as a3 into xtr cube plus a2 into xtr square plus a1 into xtr plus b plus r, where r is a random array generated using the random state function. Now we can plot xtr versus ytr and x versus y, which gives the plot as shown in this figure, where we can see these red dots as the training data, and this black curve is corresponding to the actual output data. Now our objective is to find a polynomial function for which the predicted output closely matches with this black curve, and to find this function we will be using this training data. Now to fit a polynomial function to this input output data, we will be using the polyfit function from the NP library. xtr and ytr will be the training input and training output, and here we have to specify the order of the polynomial function as an input argument, and here we are taking the order as 3. Then the polyfit function will find the coefficients of the polynomial using the training data. To see that, we can run this line, which gives the coefficients of the polynomial as 0.019, 0.104, 0.513, and 1.69. Then we can use the poly1d function from the NB library to construct a polynomial with the coefficients as given by this polyfit function. So here the output of this polyfit function will be the coefficients of the third order polynomial, and this acts as the input of this poly1d function. we will be denoting the trained polynomial function as model underscore p. Then we can use the trained polynomial function or model underscore p for predicting the output for the input data x, and we denote the predicted output as y underscore p. Then we can plot xtr versus ytr and x versus y and x versus y underscore p, which gives the plot as shown in this figure. Here, this red dot corresponding to the training data and the black curve corresponding to the actual output data, and this green curve is the predicted output data. So here we can see that the predicted output is closely matches with the actual output. Now we can also see the trained model by printing model underscore p, which gives the polynomial as shown here. So the model or the polynomial function will be in the form of 0.019 x cube plus 0.104 x square plus 0.513 x plus 1.69. So we had our actual model was in the form of 0.02 x cube plus 0.1 x square plus 0.5 x plus 2. So here we can see that the trained parameters are closely matches with the actual parameters. Next, we move on to another example in which we try to fit the data generated from an exponential function using a polynomial regression model. Here, the training input consists of 10 equally spaced data points between 0 and 1, and the training output is generated using the exponential relation, which gives ytr is equal to e raised to 2 xtr plus 0.5 r, where r is a Gaussian random variable. Now we import the libraries numpy and matplotlib, and the input data x is defined as 100 equally spaced data points between 0 and 1, for which the output y is defined as e raised to 2x, where this exp function from the numpy library implements the exponential function. Here we consider this as the actual model and this y as the actual output. Now to generate the training data, we will be adding some randomness to this model, and the training input xtr is defined as 10 equally spaced data points between 0 and 1, and the training output ytr is defined as e raised to 2 xtr plus 0.5 r, where r is a random array of size 10, which is defined using this random state function. Now we can plot xtr versus ytr and x versus y, which gives the plot as shown in this figure, where this red dot shows the training data and this black curve shows the actual output data. Now our objective is to find a polynomial function for which the predicted output closely matches with this black curve. And for that, we will be using the polyfit function as in the previous example. And the polyfit function uses the training data xtr and ytr, and it fits a polynomial to this data for which the order can be specified as an input argument. So here we are specified the order as 3. And then this model underscore p will be a third order polynomial for which the coefficients is computed using this polyfit function. And then using the model underscore p, we can predict the output for the input data x, and the predicted output is denoted by y underscore p. Now we can plot xtr versus ytr, x versus y, and x versus y underscore p, which gives the plot as shown in this figure, where these red dots are the training data, and this black curve is the actual output data, and this green curve is the predicted output data. Now, if we change the order of the polynomial, we can see that the model underscore p will also changes, and thereby the predicted output will also changes. For example, if we change this to model 0, then we are trying to fit this data with a 0 order polynomial, which gives a constant function, and the predicted output will be as shown in this figure, which basically gives the mean value of the training output. Now we can try to fit this data with a first order polynomial, which gives the predicted output as shown in this figure, where we can see a line. Now we can change this to order 2, which gives a quadratic function. And similarly, we can change this order to different other values and see how this predicted output changes. We have seen that by changing the model order, the polynomial function or the predicted output will changes. So next, we can analyze the effect of the model order or the order of the polynomial in the prediction accuracy. For that, we repeat the same example with the order ranges from 0 to 9, and we name the models from model underscore P0 to model underscore P9. Then for each of these models, we can predict the output for the input data X, and the predicted outputs are named as Y underscore P0 to Y underscore P9. Next, we plot XTR versus YTR, X versus Y, and X versus Y underscore P for each of these models. So we plot Y underscore P0 till Y underscore P9. Here we will be having 10 subplots, and these subplots are arranged in the form of 2 rows and 5 columns. Now, if we run this, we get the plot as shown in this figure. And here we can see that as we increasing the model order, the prediction performance improves initially. However, as we increasing the model order, later on the performance is getting affected. Here for order 8 onwards, the predicted output is very much different from the actual output. And the reason behind this behavior is overfitting. Overfitting normally happens for polynomials with a large order. And this overfitting can be clearly observed in the 9th order case, where the model is trying to exactly fit the training data. However, the training data contains noise or uncertainties. So here this model is trying to fit the noise pattern in an exact way. And it may result in a polynomial with large values of the coefficients, so that the training error is 0. In this case, if we consider some new input data other than the training data, the predicted error will be more, which means the output predicted by this model and the actual output will be different. Therefore, in the case of overfitted model, the training error might be 0 or considerably small. However, for a new data or testing data, this model may give inaccurate predictions. By overfitting, here we means the model is overly fitting on the training data. And this mostly leads in underfitting on the testing data or the validation data. And this we can see by considering a new set of data, which we name as the testing data here. And we denote the testing input XTS as 10 equally spaced data points between 0.05 and 1.05. And the testing output YTS is defined as e raised to 2 XTS plus 0.5 R. Now we can predict the output value for the training data for each of these models. And this predicted output we name as Y underscore PR0 to Y underscore PR9. And similarly, we can predict the output for the testing input for each of these models. And these predicted outputs are named as Y underscore PS0 to Y underscore PS9. Then we are trying to find the error in the training and testing cases. And for that, we will be using the mean square error function. And here this MSC underscore TR denotes error in the case of training data. And MSC underscore TS denotes the error in the case of testing data. Now we can compute this error for the model order varies from 0 to 9. And we can plot MSC TR and MSC TS, which gives the plot as shown in this figure, where this first plot shows the training error and the second plot shows the testing error. Here we can see that as the model order is increasing, the training error is decreases and eventually it becomes 0 for the model order 9. However, as the model order increases, the testing error increases and it becomes very much large as the order becomes 9. So here this testing data can be used for validating the model or as a validation data. And by considering the training error and testing error, we can select the model order. Also, another way to avoid overfitting is to take sufficient number of data points in the training data. And also one can go with various regularization methods, which basically prevents the weights or the coefficients becomes too large. That leads us to the end of this lecture, and thank you.